Hello. Today we are going to present our project for SKTU 2153 Section 1 Mechanic of Material. So my name is Muhammad Syarul Irwan bin Muhammad Azur Azizan, and together with my group members Muhammad Syabil bin Syabuddin, Cik Arif Faiz bin Sairi Jasmi, Muhammad Najmi Hakimi bin Muhammad Azam, and Ahmad Muslim bin Ahmad Sabri. So we will be presenting our work. So our presentation will cover the main concept, analysis, calculation, and findings related to our project. We hope that by the end of this presentation, everyone will have a better understanding of the topic and its engineering application. Without further ado, let's begin our presentation. So first, I would like to introduce our project. So this project aims to investigate the bending behavior of a bar made from uncooked spaghetti. So the spaghetti bar was fabricated with a specific cross-sectional shape and tested by applying gradually increasing loads until its failure. So the purpose of this experiment is to understand how a material behaves when subjected to bending behavior. So throughout this project, we apply several important concepts for mechanics of material, including stress analysis, shear force, and bending moments. So we also compare the experimental result with theoretical calculation to evaluate the accuracy of our analysis. Next, I would like to explain the objective of our project. So there are four main objectives that guided this experiment. So the first objective is to compare the experimental result with the theoretical analysis and evaluate the structural performance of the spaghetti bar. So this comparison helps us determine whether the theoretical equation can accurately predict the actual behavior of structure. So the second objective is to determine the allogonal stress by using a factor of safety of 1.5. So the factor of safety is an important engineering concept because it ensures that a structure can safely withstand the applied load without reaching its failure limit. So the third objective is to analyze the structure behavior by constructing the shear force diagram and bending moment diagram. So this diagram allows us to identify the distribution of internal forces and moments along the spaghetti bar and determine the critical section where failure is most likely to occur. So finally, the fourth objective is to evaluate the bending performance of the spaghetti bar under gradually increasing load. So throughout the experiment, we observe the amount of deflection, the maximum load the specimen could withstand, and the location where failure occurred. So this observation provide valuable information about the structural behavior of the spaghetti bar. In conclusion, this objective helps us understand the relationship between theoretical calculation and experimental value while improving our knowledge of bending behavior and structural analysis in engineering.
Next, we're moving on to the material we use. We use spaghetti, rubber band, adhesive tape, super glue, ruler, marker pen, saw, and cutting board to create the bar. Now we're moving on to model fabrication method. The spaghetti strands were stacked and tied together using rubber bands, ensuring that the overall length of the bundle exceeded 30 centimeter. The bundled spaghetti was tightly wrapped with adhesive tape along its length to maintain a circular cross-sectional shape and prevent the strand from shifting during fabrication. Additional spaghetti strands were attached to any section with insufficient thickness using superglue to ensure a uniform circular bar. The diameter of the spaghetti bar was checked and adjusted to ensure it was uniform along the entire length. After the glue had fully cured, the excess length at both ends of the bar was trimmed using a saw, resulting in a final bar length of 30 centimeter.
So for the calculation, we have to measure the mass of the beam first. So when we measure the mass of beam, we get 68.5 gram, and the weight of the beam is 0.67 Newton, and the weight of load we have when we use 1.5 kg load is 14.72 Newton, and the total weight we will get 15.39 Newton. So we have to find the reaction force at A and B first. So we have a roller because they can rotate at x-axis, and we have to find the summation MA equal to 0, where we will use negative 15.39 times with 0.15 plus 0.3 RBY. So we can get the reaction force at BY, which is 7.7 Newton, and then we use the summation Fy equal to 0, and 7.7 plus with negative 15.39 plus RAY, and we will get the reaction force at AY is 7.69 Newton. For the calculation at SFD, shear force diagram, and bending moment diagram, we have to cut it into three parts, which is segment 1, segment 2, and segment 3. So at segment 1, we will use the summation F equal to 0, where we have RAY, which is 7.69 minus V, and we will get V equal to 7.69. And the summation M equal to 0, MM equal to 0. And then at segment 2, summation F equal to 0, 0 equal to 7.69 minus V minus 15.39, and we will get V equal to negative 7.7 Newton. So we have to cut it where we have to include the 15.39 Newton. And then at summation M equal to 0, we will get 0 equal to negative 15.39 times with 0.15 plus 7.7 times with 0.15 plus M. So we will get M equal to 1.15 Newton meter. At segment 3, we will get the same force, which is negative 7.7 Newton, and summation M equal to 0, we will get M equal to 0 Newton meter. So they cancel out, and we will get the bending moment diagram, which is the triangle shape, and the shear force diagram, we will get two rectangular shape. So at bending moment diagram, the maximum bending moment is 1.15 Newton meter. So for the next calculation, which is 3.0 kilogram load, we still have the same mass of beam, and the difference is the weight of load we use is 29.43 Newton. So the total weight is 30.1 Newton. So we have to do the same method as the previous one, which is summation M equal to 0 and summation Fy equal to 0. So the RBY will get 15.05 Newton, and the RAY will get the same, which is 15.05 Newton. So for the shear force diagram, we will have to cut it into three parts, where segment 1 we will get the V equal to 15.05 Newton, and the moment is 0. Newton meter. And for the next one, at segment 2, we will get the V is negative 15.05 Newton, and the summation M equal to 2.26, where is the maximum bending moment. And for the segment 3, we will get V equal to negative 15.05 Newton, and the summation M we will get 0. Newton meter. So the graph is still the same, where it's still a triangle shape and for bending moment diagram, and two rectangular for shear force diagram. So for the next calculation, for 4.5 kg load, we still have the same mass of beam, and the load of the weight is 44.15 Newton. So the total weight is 44.82 Newton. So we still have use the same method, which is summation MA equal to 0 and summation Fy equal to 0. So we will get the reaction force at B is 22.41 Newton, and summation, when we use summation Fy equal to 0, we will get the reaction force at A is 22.41 Newton. So for the shear force diagram and bending moment diagram, we will have to cut it into three parts, segment 1, segment 2, and segment 3, and we will use the summation F equal to 0 and summation M equal to 0. So for the segment 1, we will get the V is equal to 22.41 Newton, and the M equal to 0. Newton meter. And at segment 2, we will get the V is equal to negative 22.41 Newton, and the summation M, we will get the max bending moment, which is 3.36 Newton meter. And at segment 3, we will have V equal to negative 22.41 Newton, and the moment is 0 Newton meter. So still the same graph, where triangle and rectangular shape, and the max bending moment is 3.36 Newton meter. So for the next calculation, which is 6.0 kilogram load, we have the weight of load, which is 58.86 Newton, and the total weight is 59.53 Newton. So for the method, we still use the same method, where we'll get RBY equal to 39.77 Newton and RAY is 29.76 Newton. For the shear force diagram and bending moment diagram, we still have to cut it into 3 segments, where segment 1, we will get V equal to 29.76 Newton and the M is equal to 0. Newton meter. And at segment 2, we will get negative 29.77 Newton and the maximum bending moment, we will get 4.46 Newton meter. And at segment 3, we still have the same value as segment 2, which is negative 29.77 Newton, and the bending moment will have 0. Newton meter. So the maximum bending moment in this graph is 4.46 Newton meter. So for the next calculation, which is 7.5 kilogram load, the mass is still the same and the weight of load will use 73.6 Newton. So the total weight we use 74.27 Newton. The method summation M equal to 0 and summation F equal to 0. So we will get RBY 37.14 Newton and RAY is 37.13 Newton. For the shear force diagram, we will have to cut it into 3 parts, segment 1, segment 2 and segment 3, and we'll use summation F equal to 0 and summation M equal to 0. So at segment 1, we'll get V equal to 37.13 Newton and M is equal to 0. Newton meter. 0 Newton meter. And at segment 2, we will have V equal to negative 37.14 and the M we will have 5.57 Newton meter, which is the maximum bending moment. And at segment 3, we will have negative 37.14 Newton for the V and the M is 0. Newton meter. So for the graph, the maximum bending moment is 5.57 Newton meter.
Moving on to the next slide, let's look at how we establish the allowable normal stress for our test specimen. First, from our physical testing, we identified 3 critical parameters shown in the top left. A failure load of 7.5 kilograms, which translates to a failure weight of 73.56 newtons, resulting in a maximum bending moment of 5.57 Newton meters. On the left, we calculate the failure normal stress, sigma failure, using the elastic flexion formula, my over I. Using a standard specimen diameter of 15 millimeters or 0.015 meters, this calculation yields a failure stress of 1.68 megapascals. To guarantee a safe structural design under actual working conditions, we apply a factor of safety of 1.5, shown on the right. By dividing our experimental failure stress by this factor, we arrive at our final allowable normal stress of 1.12 megapascals. This 1.12 megapascal limit is the maximum stress our design can safely tolerate during operation. Thank you.
In conclusion, this project successfully investigated the bending behavior of a composite structural member using an uncooked spaghetti bar. All of the stated objectives were achieved. A round-shaped spaghetti bar with a diameter of 1.5 cm and a length of 30 cm was successfully constructed using adhesive tape, super glue, and rubber bands to maintain its shape. Using a hanging water bottle to apply the load, the bar demonstrated predictable elastic deformation before reaching its limit. The bar reached failure at a maximum mass load of 7.5 kilograms, which is equivalent to 73.56 Newton. By applying the required safety factor, SF equals to 1.5, the observed failure normal stress of 1.68 MPa was used to safely recommend an allowable normal stress of 1.12 MPa for this design, ensuring that any application remains within the structural boundary. All in all, this experiment successfully matched the theoretical concepts of internal stress, bending moment, and failure with the physical testing. This shows that the cross-sectional shape and area directly impact the ability of the bar to withstand the load.